Hi all, let us explore more about thermodynamics, and it's going to be your final chapter in semester 1. Thermodynamics deals with the transfer of heat. The first law of thermodynamics is a statement of energy conservation, and the first law of thermodynamics states that the heat supplied to a system is used to increase the internal energy and the work done on the gas. What is meant by thermodynamics? It's a study of energy relationships that involve heat and other forms of energy, such as mechanical, electrical, or chemical energy and energy transfer. State the first law of thermodynamics. It states that Q equals to del U plus W, or negative Q equals to del U minus W. Q here is the amount of heat supplied for positive Q, or amount of heat released for negative Q. Del U is change in internal energy. Positive W is work done by the system for positive W. And negative W is work done on the system for negative W. Let us try to attempt these questions by applying the first law of thermodynamics. Question 1. A system absorbs 200 joule of heat as the internal energy increases by 150 joule. What work is done by the gas? So system absorbs 200 joule, the Q should be positive, and work is done by the gas. The work is positive. By using the equation of first law of thermodynamics, the work done by the gas is 50 joule. Question 2 is about, in a chemical laboratory, a technician applies 340 joule of energy to a gas while the system surrounding the gas does 140 joule of work on the gas. What is the change in internal energy? So the technician applies 340 joule of heat, the Q is positive. 140 joule of work done on the gas, so the work is negative. So by using the first law of thermodynamics, the internal energy U is 480 joule. Simple like a bubble without giving you any trouble. And the last part of the questions is about 8000 joule of heat is removed from a refrigerator by a compressor which has done 5000 joule of work. What is the change in internal energy of the gas in the system? Heat is removed from a refrigerator, so the Q definitely going to be negative 8000 joule, and the work going to be negative as well, 5000 joule. Again, by using the first law of thermodynamics, the internal energy U is negative 3000 joule. Piece of cake. You just need a cup of coffee at this moment. In this part, we're going to see the expansion of the gas. An expanding gas always does positive work. The arrow shows the gas is expands, where volume 2 is greater than the volume 1, or final volume is greater than the initial volume. And the area below the graph shows that the work done by the gas and the work done is positive work. The question is how to find the area of this graph so that it is equals to work done by the gas and it is positive work. Mathematically, we can use this formula to find the work done by the gas. Work done equals to nRT ln V final over V initial, or work done equals to nRT ln V2 over V1. For your PSPM syllabus, you just have to use this formula or apply this formula without knowing how to derive it. Or you can put the formula into this way for the constant temperature by applying Boyle's law. The work done is equals to nRT ln P initial over P final, or work done equals to nRT ln P1 over P2. So by applying the Boyle's law here, it is crystal clear that this process of expansion is occur at constant temperature. And how about the compression of the gas at constant temperature? We're going to do the same process like what we did for the expansion of the gas. But only one thing differ between these two is about final volume and initial volume. For the compression, the final volume is less than the initial volume. And definitely the work done gonna give you negative value, and the work done is the area below the graph. Or we call it work done on the gas. So we just have two terms here, work done by the gas or work done on the gas. So work done on the gas is negative. So the graph shows the arrows is compressing. So the volume is decreasing. So mathematically we can use again this formula where work done equals to nRT ln V final over V initial, or work done is equals to nRT ln V1 over V2. Exactly like before for the process of expansion, we can rewrite the equation into this form for the constant temperature where we are applying Boyle's law. So the work done is nRT ln P final over P initial, or work done is equals to nRT ln P2 over P1. Please take note that these compression of a gas occur at constant temperature. So for the expansion and compression, you're going to get one curved line. For the next part is about expansion of the gas at constant pressure. So for the constant pressure, for the process of expansion, you're going to get a straight line. And again, the area is the work done by the gas. The work done is positive because of the final volume is greater than the initial volume. So mathematically, the work done is equals to area below the graph. So the area is pressure times the change of volume. So we'll get positive work as the answer. And we're going to do the same process for compression, and you will get the work done on the gas is negative. Once we understand all the terms that we used in first law of thermodynamics, like heat, change in internal energy, and work done by the gas and work done on the gas, happily we can enter the process of thermodynamics. State 4 common processes of thermodynamics. The first one is about isothermal process. It's a thermodynamic process that occurs at constant temperature where change in internal energy is equal to 0. By applying the first law of thermodynamics, you will get Q equals to W. And the next one is about isovolumetric or isochoric process. It's a thermodynamic process that occurs at constant volume where work done is equal to 0. Again, by applying the first law of thermodynamics, the Q is equals to del U, or change in internal energy. And followed by isobaric process. It's a thermodynamic process that occurs at constant pressure where heat, change in internal energy, and work done is not equals to 0. And finally is about adiabatic process. It's a thermodynamic process that occurs without the transfer of heat, or no heat will transfer in or out of the system. So the amount of the heat or Q equals to 0. And for the adiabatic process, the change in internal energy equals to negative work. Let us put all the thermodynamic processes into one axis, where path A to B is isothermal process. For path A to B, the gas is expanding. the volume is increases, so the work done by the gas. And the temperature at B and A is remains same. For path A to C is adiabatic process, where the temperature at C is less than temperature at A. No heat will transfer in or out of the system where the Q is 0. For path A to D is isobaric process or isovolumetric process, where the temperature at D is less than temperature at A. Eddies occur at constant volume, where the work done is 0. And finally, for the path A to E is about isobaric process, where the temperature at E is greater than the temperature at A, and it is occur at constant pressure. Thank you for watching this video. Thanks a lot, and thank you to the lot.